Hi students, welcome back to Abhyaas IIT Prep channel. So today we will be seeing the questions of the chapter Atomic Structure, and we have already uploaded a video containing the questions of atomic structure, and it was the questions of April shift. So today we will be dealing the questions of January shift which came in 2024 JEE Mains. So this is our JEE Mains 2024 previous year question series. Hope you are following that. So we will move to the question. The first one. The first question is that we have to find which is a graph which is showing the correct relationship between lambda and momentum. Right, wavelength and momentum. So you know that how can we relate this particular wavelength and momentum? We have this particular de Broglie hypothesis. So do you remember, we know that lambda, de Broglie wavelength is given by lambda is equal to h by p, right? Lambda is equal to h, what is that? Planck's constant divided by momentum. So here we know that lambda will be inversely proportional to this particular momentum. Lambda is inversely proportional to momentum. So here suppose we have lambda on the y-axis, then on the x-axis you will be having momentum, and it will be inversely proportional. So if it is inversely proportional, what will be the graph? We know that whenever it is inversely proportional, it will be a rectangular hyperbola, right? Rectangular hyperbola. So you see in y-axis we should have this particular wavelength lambda, and x-axis we should have momentum p. So which is the right graph among these four? You can see that rectangular hyperbola, you are having lambda and p in the first graph. In the third graph also it is rectangular hyperbola, but it is 1 by p, lambda to 1 by p. So our answer will be the first one. So here we have used the principle of de Broglie hypothesis for finding out the answer. Hope you have understood that. Now we will move to the second question. So here, the second question, the number of radial knots for 3p orbital. So here we have to find the number of radial knots. So what is the formula for number of radial knots? You have number of radial knots equal to n minus L minus 1. So n is what? It is principal quantum number, and L is what? Azimuthal quantum number. So you have which orbital? We are having 3p orbital. So 3p means 3 is the n value, and L value for p is 1. You already know S0, P1, D2 and F3. So what will be the n value here? It will be 3. L value will be 1 minus 1. So you have 3 minus 2. So the answer is 1. So the number of radial knots for 3p orbital is what? 1. So your correct option is option 1. Right. Now the next question. Here they are asking about the magnetic moment. We have to find the magnetic moment of this following configuration. So here, first of all, we have to see how many number of unpaired electrons are there in this particular configuration. So you can write here, it is 3d7. So 3d7 means you will be having 5 orbital for 3d subshell, right? 3d subshell, you will be having 5 orbitals, 5 orbitals. So here 1, 2, 3, 4, 5. So 3d7 means there will be 7 electrons filled. That means there will be 3 unpaired electrons. So 3 unpaired electrons. You will be having 3 unpaired electrons. Now going to 3d8. 3d8, the same 5 orbitals. Now 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. That means you have 2 unpaired electrons. Initially it was 3. For the above configuration it was 3 unpaired electrons. Here you have 2 unpaired electrons. 2 unpaired electrons. Now going to the third one and fourth one. The same manner we can find how many number of unpaired electrons are there. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it is 3d3. 1, 2, 3. So you have 3 unpaired electrons. Here it is 3d6. 1, 2, 3, 4, 5, 6. So you have 4 unpaired electrons. So here students, you can easily conclude which will be having the maximum magnetic moment. It is a shortcut for you. The thing is that if you have maximum number of, whichever configuration is having maximum number of unpaired electrons, that will be having the maximum magnetic moment. We will just see how it is. So there is a formula for magnetic moment. What is that? Root of n into n plus 2. Mu is equal to n into n plus 2. Root of n into n plus 2. So n is unpaired electrons. So here you will be getting 3 electrons. So it will be what? Mu is equal to 3 into 3 plus 2. So what is that? Root 15. First one, root 15. Second one, you will be having mu is equal to what? 2 into 2 plus 2. That means it will be 8. Root 8. Then you will be having the third one again, root 15. Then the last one, 4 electrons are there. So mu is equal to what? 4 into 4 plus 2. 4 into 4 plus 2. That means 4 into 4 plus 2, 6. 4 into 6, root 24. You know that when you take the root value, which will be having the maximum number, like maximum value, root 24. Root 24. That means 4 unpaired electrons. The configuration which is having 4 unpaired electrons will be having maximum magnetic moment, because you know root 24 value will be the maximum. Whatever it is, whatever the value is after solving, you will be getting something around 4 point. But you know that it will be the highest among this. So what is the shortcut method? You just see which is having the highest number of unpaired electrons. That configuration will be having the highest magnetic moment. So which is our answer? Our answer will be the fourth one. Right, our answer will be the fourth one. So the shortcut method is what? You just see which is having the highest number of unpaired electrons. That will be having the maximum magnetic moment. I hope that is clear for you. Now we will go to the fourth question. So what is the fourth question? Here this is actually a question which is related to your coordination compounds, but they have asked the magnetic moment. So magnetic moment will be also coming in atomic structure. So we will see how to solve this particular question. So here you have to take the compound, coordination compound FeF6 3 minus. So here FeF6 3 minus, you have to see what is the oxidative state of the central atom. So here Fe we will be putting as X, and you know that F will be having, right, fluorine will be having a -1 charge. So 6 into -1 is equal to 3. You know how to find the oxidative state, right? So here X plus -6 is equal to 3. That means X is equal to it will become what to say, here it is -3, so 6 minus 3, right? You have 3 minus, so it is -3. So X is equal to what? 3 plus 3. So in the first case, here you have +3 oxidation state for this particular ion. Then for vanadium, that is Q. Q is equal to what? V H2O 6 2 plus. So here vanadium's charge X. So here H2 is a ligand, it will be having 0 charge. So X plus 0 is equal to +2. That means X is equal to what? X is equal to +2. So vanadium is having a +2 charge. Now for iron in the third case, so here again X plus H2O is 0. So it is having no charge, so it is 0. 0 is equal to +2. So here iron is also having +2 oxidative state. Now what we have to see, in the last case we have seen that how we have found the number of unpaired electrons. In the same manner we have to see which metal here is having the maximum number of unpaired electrons. So that particular metal will be having the maximum magnetic moment. So here you see iron, Fe, right? Fe, it's not Fe, it is Fe 3 plus, right? Fe 3 plus. That means from the usual configuration is what? 4s2 3d6, but 3 is missing now, right? So it will become what? 3d5, right? 2 will be gone from S, 1 will be going from D. Now we go to vanadium. V 2 plus, right? Usually it is what? 4s2 3d3, but you know that 2 electrons will be gone, so it will become 3d3, right? So here 2 electrons will be going from s orbital. Now again Fe2 plus, the third one, right? P Q R. So what will be the configuration? Normally it is 4s2 3d6, but 2 will be going, then it will be 3d6. Now you see how many number of unpaired electrons are there. So here you know that 5 orbitals are there, and there will be 5 unpaired electrons because it is 3d5. Here how many unpaired electrons will be there? It will be 1, 2, 3, and here 1, 2, 3, 4, 5. So here 6 electrons are there. 1, 2, 3, 4, 5, 6. Now how many unpaired electrons? 4. So here you have 5 unpaired electrons. Here you have 3 unpaired electrons. And here you have 4 unpaired electrons. That means we can say the magnetic moment now. In the previous question I have told you, if the number of unpaired electrons are more, the magnetic moment will be the highest. So here P is having the maximum number of unpaired electrons. So P will be having the maximum magnetic moment. Then, which is the next one having maximum number of unpaired electrons? It is R. So we have to say R will be having the second highest magnetic moment. And the least will be for Q. So this is our order of magnetic moment. P, R, Q. Right. So which is the right answer? We have won P as the highest one, R as the second highest, Q the least. So the third will be our answer. So here also the thing is that you have to find the oxidative state of the metal in that particular coordination compound. After that you have to see how many unpaired electrons are there in that particular metal. Then you can get the answer. You can conclude which will be having the maximum magnetic moment. Right. Now we will move to the next question. So here is an easy question for you. It is about the atomic number and the electronic configuration. So here, what is the question? We have to find the electronic configuration of neodymium. Okay, neodymium. So neodymium, you have the atomic number as 60, right? So first of all, we have to know which is the noble gas which is close to neodymium. So we know that we are having helium, neon, argon, krypton, then you have xenon, then you have this particular radon. So here the atomic number also we have to know 18, it will be 30, 6, 54, 86. So close to neodymium you are having xenon, which is 54. So you know that I'm saying a shortcut method. You know that xenon is 54, right? So 54 plus 6 will be giving you 60. So you just see whichever configuration after xenon is giving you 6. So you can see F4 plus 2, it is 6. That means it will be 60. Others actually they are having a problem here. 4 plus 2 it is right, it is 6, but here it is 8. Here also it will not be properly coming. So it is between this first and second. And you know that as it is particular neodymium, it will be 4F4, 6S2. You know the position of this particular neodymium. And we can conclude it will be 4F4, 6S2. Right. So it was an easy question for you. Now we will go to the sixth one. The number of electrons present in all the completely filled subshells having n is equal to 4 and s is equal to plus 1 by 2. This question, what we have to see? We have to see all the orbitals of fourth main shell. So fourth main shell will be having which all orbitals? It will be having 4s, 4p, 4d and 4f, right? There will be four subshells for this particular fourth main shell. And in 4s, how many orbitals will be there? You know that one orbital will be there. For p, there will be 3 orbitals. And 4d, there will be 5 orbitals, right? And 4f, there will be 7 orbitals. 1, 2, 3, 4, 5, 6 and 7. 1, 2, 3, 4, 5, 6 and 7. So they are asking, in these orbitals, how many electrons will be having plus 1 by 2 spin? You know that in an orbital, you will be having an electron with plus 1 by 2 or minus 1 by 2. So here, in this orbital, there will be one electron with plus 1 by 2. Here 1, 1, 1. Here also 1 will be there in each orbital. And you know that this all will be having positive spin. Then the other will be having negative spin. So just count. Here it is 1 plus 3 plus 5 plus 7. So what will be your answer? 1 plus 3, 4. 4 plus 5, 9. 9 plus 7, 16. So we can say there will be 16 electrons which will be having plus 1 by 2 spin in the fourth main shell, right? The next question. The total number of ions from the following with noble gas configuration. Again, it is a question related to the electronic configuration. And for this question, obviously, we have to know what are the noble gas configurations. So again, I will be writing that list. You have helium, neon, argon, krypton, xenon, radon, right? So helium 2, neon 10, argon 18, krypton 36, 54, 86, right? Now you see here we are having Sr2 plus, and what is the atomic number? 38. So the original atomic number is 38, but it is 2 plus 2 electrons lost. That means it will be having 36 electrons, right? So the Z value become 36. So it is actually the electronic configuration of krypton, right? Krypton is equal to 36. So Sr2 plus is having noble gas configuration. Now Cs plus. So what is Z value? 55. So original number is 55, but it has lost 1 electron. So it will become 54. So that is what xenon's electronic configuration. Now you are having La2 plus. La2 plus means originally it is 57, but now it is 55. Is 55 any of the electronic configurations? No. Then we are having Pb2 plus. Pb2 plus you have Z is equal to 82. So it will become 80. So we don't have any noble gas with 80 electronic configuration. Then Yb2 plus, I am not writing it, you know that Yb2 plus will be 68. Do we have 68? No. Fe2 plus 26, that means 2 electrons lost, 24. We don't have 24 also. So that means Sr2 plus and Cs plus will be having the noble gas configuration among all the ions given. So the answer will become what? 2. 2 is our answer. 2 is our answer. So it was actually a kind of easy question for you people, right? Now we will move to the next one. So the important thing is that you should know this particular noble gas configuration or that particular atomic number of noble gas, because it is repeatedly asked many times. The questions related to the noble gas configuration or atomic number of noble gas. So you should be aware of the configuration or the atomic number of noble gases, right? Now the 8th question. Here it is related to the quantum number. So here also you should be able to write the electronic configuration. So they are actually asking the correct set of 4 quantum numbers for the valence electron. Valence electron will be the 37th electron in the case of rubidium. So what is the quantum numbers for that 37th electron? So here first of all we have to write the electronic configuration of rubidium, right? So Z is equal to 37. How will you write? 1s2, 2s2, 2p6, 3s2, 3p6. How many filled? 4, 10, 18, right? So we can go for 3d 10. 4s2. So here it will be what? It will be 4s2. Again, we have to go for 4p6. Then it will be 5s1. Okay, it will be 5s1. So the last electron, right? Here it will be the 37th electron, and it will be going to 5s1. So 5s1 means principal quantum number n is equal to 5. Azimuthal quantum number L is equal to what? 0. So here 5, 0, and for S, ML value is what? 0. That means I have 5, 0, 0 plus 1 by 2. So here what will be the answer? 5, 0, 0 plus 1 by 2. The first option will be your answer. Right. Now to the next question. Here it's a matrix based question, and we have to find the region of different spectral series. You know that the simplest way to solve this problem is that, first we have discovered this particular Balmer series, and Balmer series was actually in this particular visible region, right? And also we know that Lyman, the next one, is actually in what? The UV region, right? So the others can be easily matched, Paschen to infrared and PFED to infrared. So which will be the answer? B. B to the fourth one, B4. So B4 is actually having only in the third option, right? A2, what is A? A is to the UV region, right? Then you are having Balmer to the fourth one, visible region. Then C3, Paschen to infrared, and D1, PFED to infrared, right? So with that single knowledge, that particular knowledge, what is that? This particular Balmer series belong to this particular visible region. We can solve this question, right? Now the next one, you are having two statements, and we have to say whether both the statements are true or false. First statement, that the orbitals having same energy are called as degenerate orbitals. Yes, we call the subshells having the same energy, or orbitals which are having the same energy as degenerate orbitals. It is a true statement. Now the second one, in hydrogen atom, 3p and 3d orbitals are not degenerate orbitals. So here you know that hydrogen means it is a single electron species. So in the case of single electron species, the energy is determined by the principal quantum number. Okay, for single electron species, the energy is determined by the principal quantum number. So you know that in 3p, 3d there will be no electron. Again, in 3p and 3d, you can see what is the principal quantum number of 3p? It is n is equal to 3. What is the principal quantum number of 3d? N is equal to 3. That means for single electron species, as the energy is determined by principal quantum number, I have to say 3p and 3d will be having the same energy. That means they are degenerate orbitals. But what is the statement? In hydrogen atom, 3d and 3p orbitals are not degenerate. So this is a false statement. So what is my answer? Statement 1 is true, but statement 2 is false. Statement 1 is true, but statement 2 is false, right? Now, the next question. Number of spectral lines obtained in helium He plus spectra when an electron makes transition from fifth excited state to first excited state. So here, what is happening? Ground level or ground state will be E1, energy level 1. Then you are having E2, E3, E4, E5, E6. Right, you are having E6. So the first excited state will be what? Energy level 2. Then the fifth excited state will be what? Energy level 6. Now the electron is making transition from 6th to, second energy level. So what is my delta n? My delta n is 6 minus 2, it is 4, right? So the delta n value is 4. How? from 6 to second, right? So 6 minus 2, it is 4. Now, if I want to know the number of spectral lines, the formula we know that delta in into delta n plus 1 by 2. So what is that? It is 4 into 4 plus 1 by 2. So it will be 4 into 5 by 2. That means 10. Right? 20 by 2, 10. So I will be having 10 spectral lines when the electron is making a transition from 6th excited state to 2nd excited state. I hope you got how we arrived at the answer. Now we will move to the 12th one. So here in the 12th question, the ionization energy of sodium in kilojoule per mole we have to find. So what is happening here? You are having the sodium atom. Now a particular wavelength is hitting, a radiation of wavelength 242 nanometer is actually hitting this particular atom, and the electron is being ejected, right? So they are asking, we have to find the ionization energy. You know that the energy required to remove an electron. So when this wavelength is hitting this particular atom, that radiation, right, having this certain 242 nanometer wavelength is hitting this particular sodium atom, what is happening? The electron is being ejected. That means we have to find the ionization energy, and we have given this particular wavelength. So how will you solve this question? You know that E is equal to H nu. So we can write nu in terms of lambda. What is lambda? What is that? H is equal to C by lambda. So here I can write. So we are finding the energy, ionization energy. So H is what? Planck's constant, 6.6 into 10 raised to minus 34. Now C, you know that 3 into 10 raised to 8 meter per second. So here lambda value is what? 242 into 10 raised to minus 9 meter, right? Nanometer. So you will be getting, when you are solving this, you will be getting an answer of 8.18 into 10 raised to minus 19. Okay, this will be actually what? The energy that we will be getting. Now, this is actually energy per atom, right? This will be the energy per atom. But we have to find what? The energy per mole. So you will be getting what? 8.18. You will be getting 8.18 into 10 raised to minus 18, right? Now we have to convert it into what? Per mole. That means it will be into 6.022 into 10 raised to 23. So you will be getting at last 493 kilojoule per mole. So here your answer is what? 493 kilojoule per mole. Okay, so what we have done, we have multiplied this particular energy per atom into one mole of atom, that is Avogadro number of 10 raised to 23. Okay, this is 10 raised to 23. Right, now moving to the last question of this particular shift. The 4 quantum numbers for the electron in the outermost orbital of potassium. So potassium's electronic configuration, we should know what is the electronic configuration of potassium. What is that? 1s2, 2s2, 2p6. You will be having 2p6. Then we know that 3s2, 3p6, 4s1, right? 4, 10, 12, 18, 19. So 4s1 is the last orbital. So 4s1, n value is what? 4, L value is what? 0, ML value is what? 0, and MS will be plus 1 by 2. So here my answer will be 400 plus 1 by 2. So 400 plus 1 by 2. So the second option is my answer. So here we have come to the end of the last question, right? End of the session. And in this session we were actually discussing the questions of January shift of 2024 JEE Mains. So I hope you have understood the questions and answers that we have discussed here. Follow more videos in our channel. We are having a special series running, that is previous year questions of JEE Mains 2024. So watch out for more videos. Thank you for watching.